she's ready to go. Our first presenter is Alexandria Podolski. She's a research analyst at Applied Research Associates. You heard from some of those folks yesterday as well. She leverages her background in engineering to act as a jack of all trades. Must be a Jill of all trades. She has contributed to a variety of projects in health effects and risk assessment research, in addition to oil spill research. Alexandria has performed extensive lab work, field work, and data analysis to assist in quantifying the effectiveness of herders and dispersants using the Baffled Flask test on a lab scale, as well as in situ burn rates and efficiency for several different types of oil. And today she's going to be speaking to us on characterizing the effects of oil viscosity and SARA, S-A-R-A, on dispersant effectiveness. I'm sure she'll tell us what SARA means. And she will have some of her colleagues standing by and ready to assist with some questions. So you may also be hearing from Paul Panetta and Rick Byrne as she goes through her presentation. So let's turn it over to Alexandria.
All right, here's the moment of truth. Can you see me?
We can see your camera.
All right.
We can see you.
Can you see my presentation?
Not yet. Sometimes it takes a little while after you hit share screen for it to pop up.
Yeah, no kidding. All right, let's see here. Let's give it one more go.
Oh, you're getting closer.
Okay.
There you go.
All right, all right. And now
we're good.
Finding the mouse. All right, how's that?
That's good.
Excellent. All right, like Ellen said, I'm Alexandria. This is my first time presenting here, but you've heard from two of my colleagues on in situ burn and herder effectiveness. So it's only natural that I'd round it out and talk about dispersant effectiveness. I'll give you a quick background on dispersant use, historical dispersant use, and then the oil properties we used during our testing, our test matrix, a quick overview of the Baffled Flask test, and then an overview of list measurements, which we compared to that Baffled Flask test. Finally, we'll go with a summary of our results and future work. I'd be remiss if I didn't mention that this work was funded by Bessie under project number 1073. So if this is your first day, then maybe you haven't heard all of the different locations and conditions oil spills occur under, but lots of different types of oils varying in properties, both physical and chemical. So dispersants are used as an alternative to herding and burning and mechanical recovery. So while burning is super efficient, super quick, herding, both mechanical and chemical, it draws out that oil into a specific spot. Dispersants actually do the opposite of that. So kind of like when you put oil in a pan after frying something and all the oil to the edges of the pan, dispersants break up droplets small enough that they're able to be pushed underwater into the water column. So dispersants were used in unprecedented qualities in Deepwater Horizon. They actually used about 1.84 million gallons of dispersant. But despite that prior use, the relationship between dispersant effectiveness and then the properties of the oil that's been spilled needs to be more thoroughly studied. So we developed an extensive test matrix. So we looked at 10 different crude oils and we performed Baffled Flask tests for those 10 oils with 2 different dispersants. So Corexit 9500A was one of the 2 dispersants used in Deepwater Horizon. And we compared those results, that dispersant effectiveness results to the dispersant effectiveness results of Finisol at 2 different temperatures. So that's a total of 10 oils, 2 temperatures, and 2 dispersants. And we looked at those Baffled Flask test results, and we also compared those results to list measurements of dispersant effectiveness. Slightly different, but also indicative of how the oil is being broken up after dispersant application. In addition to those two measurements, we looked at acoustic measurements just to continue developing some techniques for additional measurements. So like I said, we looked at 10 different oils. Those oils varied drastically in physical properties. We looked at Anadarko, which was just 11 centipoise at 20 C, all the way up to Platform Gina, which at 20 C was 3,244 centipoise, so a magnitude of 300 times more viscous. So those oils, again, they're broken out into light, medium, and heavy crudes, wide range of properties to test that dispersant effectiveness. So in addition to those physical properties, we looked at chemical properties of the oils as well. So in our chemical properties are broken out very simply into 4 different groups: saturates, aromatics, resins, and asphaltenes. That's the SARA and SARA. So you can see with this graph here that the SARA properties were maybe similar in a couple of the oils, but for the most part, very, very different. So from the left to the right, we've got increasing viscosity. And there's no real clear pattern that emerges. There's none of these components directly correlates with viscosity, which is why we were looking at the dispersant effectiveness for viscosity and then separately those SARA components. So primarily we were using the Baffled Flask test to determine the dispersant effectiveness. I want to take a moment to thank Robin Conmey for her help with getting us prepared to do those tests. So we performed a total of 216 Baffled Flask tests with that combination of oil, dispersant, and temperatures. So step 1 of the test, very simply, is mixing, followed by liquid-liquid extraction to remove the oil. And then we put that into a UV vis to measure the absorption, just to determine exactly how effective that dispersant was. So in a bit more detail, we used a baffled flask. So baffled flask is just a container for the oil with baffles much like a dryer, just to mimic that mixing energy in the ocean. So we'd mix each sample after applying dispersant on top of the oil slick at about 200 rotations per minute for 10 minutes, and then just let the sample sit for 10 minutes. So this mixing energy, critical part of dispersant function, which is why dispersants are considered only to be an effective response strategy in turbulent oceans. So next we did this liquid-liquid extraction. So poured the sample from the baffled flask into a separation funnel and applied some dichloromethane to extract oil that had been dissolved into the water column, as well as oil that was still as a particulate. We'll go into that separation a little bit more in detail later. But we did 3 separate liquid-liquid extractions. So added a little bit of dichloromethane, shook it up, allowed the oil to come out the bottom, and then did that again 2 more times. So once we extracted the oil from the sample, we put those samples into the UV vis to measure the absorption. So it's a lot of words, but in the bottom left-hand corner, you'll see we've got 4 different vials with those samples from the liquid-liquid extraction. So we take a little bit of that sample and we'd measure it against stock solutions that we'd created with known concentrations in order to determine how much oil was in that sample, therefore how effective the dispersant was at dispersing the oil into the water column. So the Baffled Flask test is a unique test in the sense that it was designed to be operator independent. So my colleague Jennifer Durding and I, we both performed these measurements just to see how comparable our results were, and they were incredibly comparable. So again, looking in this bottom left-hand corner image, we've got two different oils. We've got IFO 120, which is a high viscosity oil. And we've got on the right, Ewing Bank, which is a low viscosity oil. And that's both at 20C and 5C. So you'll notice the sample on the left for each of those oils is much darker for IFO 120 than the right sample, which is 5 degrees C, which indicates that the dispersant was much more effective at 20C than 5C. Whereas for Ewing Bank, the less viscous oil, those two samples look about the same. And we see that in our results. So this is a lot of information here, but we'll try and break it down. So from left to right, the dark green and the dark blue is going to be dispersant effectiveness of Corexit 9500A. And the light green and the light blue is the dispersant effectiveness of Finisol. And then on top of that, the green is just going to be indicating 20C and the blue is indicating 5C, blue for cold, green for warm. So from left to right, our oils are increasing in viscosity. So if we consider 75% to be a rule of thumb for dispersant effectiveness, in general, most of these oils are effectively dispersed at 20C. I would say actually most, if not all of them. Also, general trends at 20C, Finisol is generally slightly higher dispersant effectiveness than Corexit, which is interesting. For both dispersants, however, there's significant decrease in dispersant effectiveness. But we really start to see that significant difference for the medium to heavy crudes. So these first three here on the left, those are lighter. These next three are medium, and these last four are heavy crudes. So there's a general overview of the viscosity results. We looked at the correlation between dispersant effectiveness and viscosity for each of these dispersant temperature combinations. And interestingly enough, despite high dispersant effectiveness at 20C, the linear relationship between viscosity and dispersant effectiveness was actually not very strong. It was significantly stronger at 5C for both different dispersants, but the highest R-squared value we saw was 0.82 for Corexit at 5C. So not as high as we might anticipate. That being said, it was significantly higher than the relationship between the SARA components and the dispersant effectiveness. These visually, you can tell they're just kind of all over the board. Most of them had an R-squared value less than 0.5, which is not strong at all. In fact, the highest we saw was R-squared values of 0.7 and 0.75 for aromatics and resins for 20C and Finisol. So the main takeaway here is that although we like to lump a lot of chemical components into these four categories when we're considering the chemical makeup of these crude oils, SARA is probably an oversimplification of the chemical properties, and we really need to look into chemical properties in more depth. Like I mentioned before, in addition to those Baffled Flask measurements, we did list measurements of dispersant effectiveness. List measurements are a little bit different. So as a community, we consider dispersed oil to be both dissolved oil, so very, very tiny size particulates, and well, I would say tiny, tiny bits of oil in the water, and then particulates of oil, which are big enough to scatter light. So the list measurement only measures particles that are big enough to scatter the laser, where Baffled Flask takes into account both the particles that are too small to scatter light and particles that are big enough to scatter light. So these list measurements were, it should be noted that they were also taken on the exact same samples that were resultant of those Baffled Flask tests, just so they were as comparable as possible. So we did 4 different repeats of these measurements. So anything that's less than 70 micrometers is considered dispersed. So the list can actually measure particles in between 1.5 and 500 micrometers. So anything here to the left of this black line is considered dispersed. What you'll notice is that the dispersant effectiveness as a result of those Baffled Flask tests is much, much higher than the dispersant effectiveness by the list. And again, that's just because of that breakdown of what types of particle the list can measure. So at 20C, it appears that there's a lot more of those particles that are visible to the list, where at 5C, not so much. It's also probably good to note that small droplets that the list is detecting, while small, they're still potentially big enough to coalesce, which means that the list measurement of dispersant effectiveness could potentially be artificially elevated. So in conclusion, there is a general correlation between viscosity and dispersant effectiveness. However, it's not as strong as we might have thought. And while asphaltenes may have the highest correlation out of the SARA components with dispersant effectiveness, it similarly is not as strong. In fact, it's significantly lower than the correlation with viscosity. Dispersant effectiveness is also temperature dependent, which is pretty important when deciding what type of response tool to use based on the environment. And finally, as we're continuing to advance measurements or work on measurements translating from the lab into the field, looking at measurements like Baffled Flask that are potentially much higher than field measurements like that of lists, it's important to keep in mind that they're not directly comparable. But when used together, they can help inform responders' decision-making. All of these results are summed up in our final report. You will have this link that you can access those results at. So future work, like I said, SARA components might be an overgeneralization, but we could potentially get more detailed information if we did GC mass spec on these different crude oils. Important to consider that those properties change as oils are emulsified and or weathered. So it might be of interest to look at those chemical properties under different weathering conditions as well. And also performing these similar lab scale tests with field scale in situ style tests as well. So sampling water at onset, performing those same liquid-liquid extractions and list measurements. And instead of having the Baffled Flask component to perform the mixing energy, actually using that wave energy in a large tank. So like Ellen and I had mentioned earlier in this presentation, we're looking at all kinds of response methods. These are the 3 that my colleagues and I have focused on primarily. So we've got in situ results for, I would say, about 25 different oils and weathering states. We've got herder efficiency for 14 of those, and we've got dispersant effectiveness of 10 of those. So as we continue to perform research, we're filling in more and more of this table. We're having more and more insight as to what response methods should be used under all these incredibly varying conditions. There's definitely some room for filling out, I would say, this the dispersant efficiency for weathered oils. It definitely seems like that's the direction we're moving in as a community. But that's about all I've got. So you look at that, on time.
You did good.
Thanks.
There was a question in Q&A for you. I jumped ahead and answered it.
Oh, perfect.
And if we don't have any other questions, I can review that for you, so you can you and the others will know how I responded. But Lindsay, do we have any other questions for Alexandria?
No other questions, but Tim Nedwood just dropped a comment in the chat I need to read. So go ahead and go over your question.
The question that was asked, it was asked by Susan Caralla, who is the coordinator from the Coast Guard that works with our RT9. And she asked if California OSPR had reviewed Finisol as a dispersant. And we have a separate licensing program in California, which Susan is aware of. And we'll review any product under those licensing procedures that we receive an application for, but we haven't received an application from Finisol. So it's not yet on our list of licensed products for use in California waters.
Excellent. Well, thanks for answering that for me.
And I can read Tim's comment if you'd like.
Yeah, go ahead.
Tim Nedwood comments, the 70 micron droplet size rule of thumb for effective dispersion is an oversimplification. A better rule would be based on droplet rise velocity. A partial reason why the correlation between effective dispersion with the LISST and Baffled Flask test is the density of the more viscous oils. They have lower rise velocity for a given droplet size compared to the lighter oils, and therefore somewhat larger droplets can be effectively dispersed.
Wow, yes, I would absolutely agree with Tim. I think as a community, we tend to be moving away from those rules of thumb. So it's good to know that there's potentially a better way of doing it than just that 70 micrometer measurement.
And Paul Panetta also sort of spelled out list for us. You want to go ahead and do that as well?
Oh, I'm happy to. In fact, it's actually probably easier for me to just go backwards. So it's in the right image on top, we've got list, which is laser in situ scattering and transmissometry. Can't believe I got that right the first time.
This is why we acronym some things and then why we can't remember what the acronym stands for.
Oh gosh, yeah.
Any other
one
questions?
More question?
Okay,
yeah.
Thank you. And thank you, Alexandria. That was spectacular.
Thank you so much.
From Gina Calejo, have you done any work with SilCam or HoloCam for characterizing dispersed oil droplets?
I have not thus far. In fact, I'm not even familiar with them, but I think it would be very easy to add to that table on the end if we had access to it. Whoops.
This is Paul Panetta. If I can answer, Gina, we have not worked directly with the SilCam or the HoloCam, but of course we've had lots of discussions with the Syntemp people about combining our resulting capabilities, specifically, of course, with the list, but also comparing the HoloCam with the acoustic measurements.
We good? Everybody in with their questions and comments?
Tom Coolbaugh noted that OMSET has a SilCam.
I think we see OMSET in your future. I saw Tom reaching out. All right, thanks again, Alexandria.
Yeah, thank you.